So in this lecture, we're going to look at another pericyclic reaction. This one's called the Ene reaction or the Alder-Ene reaction. So Alder of the Diels-Alder fame. And so this is a 6-atom pericyclic reaction, which means we're going to have those nice 3 arrows kind of working in a circular, either clockwise or counterclockwise motion, doesn't matter. So 6-atom pericyclic reaction. Now what's special about this is it's where an H atom is transferred to a pi bond and a new sigma bond, usually, so it's really 2 new sigma bonds, sort of. Words can only get us so far. Let's go ahead and draw the reaction. So in this case, we're going to consider a hydrogen that is on a carbon next to, that's 2 next to, carbon that is next to a double bond. So we would call this an allyl system. Specifically, an allyl H is going to see just a typical alkene, and the hydrogen is going to be transferred. Remember, we can go in either direction. It's going to be transferred to form a new bond to the edge of the pi system. I'm going to delete those. Maybe I'll change the color so we can see. Now we're going to continue moving the arrows like we would in our 6-atom pericyclic reactions. And then there's the other site of the formation of a new bond. So we form 2 new sigma bonds. One of them is not so significant, but the other one is quite significant. That is, we have this new bond between a carbon and hydrogen. That's great. Okay, everybody likes to form bonds to hydrogen, sure. But what I'm really excited about is not that bond. I'm excited about this new CC sigma bond. That's particularly an exciting bond because forming carbon-carbon bonds is great, and when you do so by a pericyclic reaction, you get some added sort of flavor because typically these reactions don't require much in the way of reagents, reactants, acid bases, initiators, that sort of thing. For the most part. Sometimes you need a Lewis acid to promote something like this, but here's an example of an interesting reaction, at least in my view, the Alder-Ene reaction. Okay, so there's the parent reaction. Let's look at some examples of these things. Some specific, well, sort of specific examples. What I'm going to do is focus on a special hydrogen donor in this first case, and that's a phenol hydrogen. So phenol hydrogens can work where the hydrogen is transferred, and the arrows could go in either direction. Whoops, I forgot these other 2 bonds, excuse me. So it's a benzene. Now we draw our 3 arrows moving in this motion. We get a new carbon-carbon bond. I should finish drawing the structure. I really should. Here, we form a carbon-oxygen double bond. There's our other 2 bonds. And then our new CH bond is up here. Now, in many cases, there's some sort of thermodynamic driving force that kicks these things into gear already. There's not so much of an equilibrium between the 2 ene reactant and product states. So in this case, the thermodynamic equilibrium is the re-aromatization of the system where this H is lost to give rise to an aromatic product. And that's just tautomerization, really. I'm gonna move away from blue here. Let's stick to the way I have been doing things. So all this really is a tautomerization to drive towards the formation of products. I'll draw the H this way. That gives us this species. So it's sort of like an electrophilic addition in a way, but it's mediated by, at the ortho position, but it's mediated by the hydrogen transfer. And so sort of a few ways of looking at this reaction. Now, one that's a little bit more pericyclic in nature is benzyne as an ene. I'm going to call it just an ene acceptor, because it's not the allyl hydrogen, it's the thing reacting with the allyl hydrogen. Now, benzene, if you recall, is benzene with a triple bond. Now, the triple bond is highly strained, right? Triple bonds we typically like to think of as being linear in nature. And this triple bond is highly distorted so as to kind of sit within an aromatic ring. And so what we can do is consider our three arrows. They're very curly for this example, I suppose. But this then releases the strain from the benzene. So there's our thermodynamic driving force. We're not heading back to benzyne from this species. And then we transfer our hydrogen over to the other side, and we form a new CC bond to what was the benzene molecule. This is a really nice transformation for benzyne because it allows for the formation of carbon-carbon bonds without reactive species like organometallics and that sort of thing that need to be dealt with and worrying about side reactions there. Here we just have a pi system reacting with benzyne without the addition of any other reactants. It's quite a nice reaction. Yeah, so anyway, here are some examples of ene reactions. This should set us up if we want to look into this in more detail. Okay, so with that, we'll move on to just one last lecture and some final aspects of sigmatropic rearrangements.